into Google Test? Yeah. So if, like, let's just say there's only one line in the file, right? And that line contains a new line character, it should be included on the output. If there was only one line in that file and that line did not contain a new line character, then your output would not contain a new line character. Okay, anything else? Okay, so we're going to get into Google Test. We've been using it for the last couple of assignments. How many of you have found the Google Test to be useful? How many of you have found it to be annoying because it takes a long time to build? Yeah, me too. It's a trade-off. For those of you that have found it to be useful, why was it useful? Yeah. It kind of like gave you like output about what was wrong with it so that you knew what to fix. Anything else? So then my first question to you is, what's the point of testing? It's not necessarily to see what's wrong, it's to verify that your program is working as intended, right? Ideally, we would be able to prove that our programs are correct, and there are pieces of software and ways that you can write your code that can attempt to prove the correctness of your program under certain assumptions. But generally doing these proofs is extremely complex and time consuming and very difficult to do. So we settle for the lesser testing, which is like, hey, here's some things that we expect to happen. Do they happen? Right? You know, if I do A plus B and A is 3 and B is 7, do I get 10? Right? You verify that that's happening. Right? So we have some expectations. We have our code. We're just trying to verify that those things are working right. So in general, who should be writing tests for your programs? Yeah, you guys should be writing tests for your programs because, you know, you need to verify that what you're doing is correct. It's not my job. It's not somebody else's job. It's your job to make sure that the code that you're writing is right. So Google Test is for unit testing, which is basically like for testing like a single method-ish in your program at a time. And if you want to be able to use Google Test, hopefully you've looked at the CMake list files. So here's what they say to do. The first thing to do is they attempt to find the threads package on your library. This is needed by Google Test because it uses the threading library. The next is to include fetch content, which is a CMake module that allows me to pull things from the internet. Over here, we declare this Google Test as something that we need, and we say, hey, this is where it's at on the internet. The recommendation, if you look at the Google Test website, is to make the Google Test a sub-build of your project. And so we're going to be doing that. So whenever we need Google Test, we'll download it to our computer. But if we already have it, we'll skip this step. That's why some of you may have noticed the first time you ran the CMake list, it took a really long time to get the project set up because it had to pull from the internet. But then subsequent times for building at least the CMake part were a lot quicker. This is just saying, hey, here's the name of the thing that we need to get. We're going to call it Google Test. Here's where it's at on the internet. And this is the tag that I want to pull from, the master branch. Then this part right here is the part that actually downloads the Google Test if it's not there. So we get the properties of that Google Test variable we just made a second ago. And if we haven't populated, right, this thing doesn't exist, go ahead and download it. Then we add that subdirectory to our project, and this is going to go call us CMake to go build Google Test whenever we rebuild our project. And then in order to create our test, you say whatever your tester name is, your program, or your project can have multiple executables. So one of the executables here is going to be your testing project. It's going to be private, and then we need to link in gtest always. Gmock if you want to use the Gmock features, which I do recommend reading that. And then there's gtest main if you don't want to bother to write your own main function. And the main function that Google Test provides is sufficient. If you want to do something different in your main, don't link against gtest main because it has main defined inside of it. Any questions about what needs to go in your CMake file in order to get this to happen? Okay. I think we can actually skip the sides here. This doesn't really need to be done. And then there's an example for this to be shown off, and then you can also look at it on your own computer, but we'll get to that in a second. So if you want to use stuff from Google Test, you include gtest/gtest.h, and if you want to use gmock, you can include gmock/gmock.h. Most of the tests break down into like verifying that something is working as intended, and there are two checks that you can use. One is assert and one is expect. Assert will check the condition that you have, and there's different types of asserts, which you'll see in the next slide. And if that assertion fails, it'll kill the test and stop running it. The expectation will check to see that what you expect to happen happens, and if it fails, it'll mark the test as a failure, but the test will continue going on. So you would use asserts where if something breaks, I can't really continue the rest of my test. You would use expects where if something goes wrong, you want it to be recorded and you want the test to fail, but you can continue going so that you can get more failure about some other things that are happening inside the test. When you have your assert or expect statement, you can write to it just like you would write to cout to put some error message there that will show up. So here's an example. So you might assert equal that x's size is equal to y's size. And then we could, write to this outstream that vectors x and y are of unequal length if this assertion failed. This will be reported. Or here we're going to go through each of the elements in x.size, right? Because we assume that they're already the same size. And then we're going to expect that x at I is equal to y at I. And then we'll report that they're going to be different at these indices if they happen to be different. Any questions here? So some assertions, there's assert true, assert false, assert equal, not equal, less than equal, greater than, or greater than or equal to. And there's expect versions of all of those, and they do exactly what you would think. And there's also some string comparisons on Google Test. So we go to Google Test. We go to the primer. So like you can expect that foo starts with hello. So there are some things that will check for the C strings as well. A lot of these things though, like the expect that, these guys you have to use the gmock in order to work, and you'd end up using a matcher. And I thought there was some other ones as well. Some other ones that are useful are like the ones for comparing floating point values or double values. Because of the rounding issues, a value might be close enough. So you can say assert float equals or assert double equals to, and it's asserting that these things are almost equal, and they might vary a little bit in the precision. Or here you can assert near that these two values are within some absolute error. So these are different ways of checking things. And C strings, I guess we have to use the matchers to make things look good. So you can say assert that this string has this, or you can use regular expressions too to match the string matches this regular expression if you need more complicated stuff. So a basic test looks like test, the name of the test suite that you want to put it inside, then test name. The test suite is the group of tests this belongs to, so it's like your testing group. Test name is going to be the name of this particular test. And the test code is whatever code that you want to run for that test. And there should be at least one assert or expect inside that statement to signify whether this code is working correctly or not. So here's a simple test. You might have some factorial test, and you might want to test that it handles the 0 input. So we expect equal the factorial of 0 to be 1. Or here we might test some positive numbers. We expect equal the factorial of 1 is 1, factorial of 2 is 2, factorial of 3 is 6, and the factorial of 8 is 40,320. So you're just doing some basic validation that what you expect to be happening is actually happening. Sometimes you might have some common code that you're copying and pasting across a lot of different functions. What you can do is just put that code inside of a function and then just call it just like you would do with anything else, perfectly fine. Or you can put that code into a test fixture. Test fixtures are really useful for like grouping tests together, providing related methods on those specific tests that you're using a lot, as well as if you have similar data that you want to operate on every single one of these tests, it's really useful to put it there as well. So if you want to create your test fixture, which again, we'll show some examples in a minute, you have to inherit from testing : test, and then members that you want to access inside the test should either be protected or public. You can't access private members inside the test. When you use a test fixture, first it's going to set up, first it will call the fixtures constructor, then it will call setup, then it will run your test code, then it will call tear down, then the destructor for your fixture is called. A new instance of the fixture is created for each test, so that's going to prevent the tests from contaminating each other. And with this setup, you can put those things that are similar to each other in this as members of the class. One thing that's kind of interesting and may sometimes be somewhat annoying is that the constructor that gets called with a text fixture is always the default constructor, the 0 argument one. So if you have like a test fixture that has more than an argument, or a constructor that takes more than one argument, it's like never going to be called. And that's just how Google Test works, and that's something you're going to have to work around. So here might be a test fixture. So we have class, my fixture, it inherits from testing : test. Then you do your public or protected members. So you might say, like, when do you set up and when do you use constructors? Generally, you want to use the constructor and not use setup, but there might be some subtle details. See this link over here if you want to just have a little bit more information about when you should use the constructor and when you should use the setup function. So if you do have a test fixture, you use test_f instead of test. So it's going to be test_f, the test fixture class name, the test name, and then again, you'll have access inside that test to all of your public and protected members. Sometimes you might want to test some control logic. So there's succeed, which generates a success. It's not really super useful, but if you want to put it there, you can. Others fail, which will generate a fatal failure. And again, you can stream a message to it. And then there's add failure at file path line number. It's going to generate a non-fatal failure. And then it will continue on. So again, it's really useful for testing control logic. So you might have like an if statement, and you should never enter the else. And so in the else statement, you can put fail, I should never be here, so that you know that you shouldn't have gotten there. So let's look at a simple test right now. Get rid of this stuff. Okay, as that goes. So here, for example, is the Fibonacci code, which you guys have probably already seen before. So Fibonacci, works as intended. And then there's a faster version of Fibonacci. What's going on? Is different from Yeah, but I told you to delete everything. Okay, that's all gone. So nothing like too crazy going on over here. And then so over here we have our test.cbp. And so we do some very simple things. So assert equal that, the Fibonacci of 0 is 1. The Fibonacci of 1 is also 1. Fibonacci of 2 is 2. Fibonacci of 3 is 3. The Fibonacci of 4 is 5. The Fibonacci of 5 is 8. But sometimes, any questions on these tests up here that are just verifying whether things are working or not? Google Test does have parameterized tests. And so if you want to do parameterized tests, you basically have to inherit from testing with param int. And then down here, well, we'll get back into this one. He's a little bit more complicated. If we go and we look at our homework assignments, you can do it, computer. We have our test subfolder, and then over here I kind of like split up the test to be like vector tests and whatnot. So over here, here's test vector.h. You can see that it inherits from testing : test. So it is a test fixture. We have some constructors to create them and I have some other methods over here like loading a vector from a file because I put a lot of my input into files. And then I have some other operators defined down here for comparing like a matrix vector with a vector of doubles to see if they have the right values. So over here are some constructor tests, or say test vector.cbp. Come on. So over here, I've defined operator equals. And so I actually had to go through and write a test that would look through and make sure that everything is correct. You can have functions that instead of like returning true or false for succeeded or not, they return a testing assertion result, which can allow you to like put a succeed or fail in there and then write to it. So the first thing that I do is in the equals, I check to see, hey, is the size the same? And if the sizes aren't the same, I complain about it. And I make sure that I return a failure. Then I'm going to assume that all of the elements match. And then I'm going to go through each one of the go through all the elements of the vectors. This right here is checking to see if the values are the same, or at least the values are within one of each other. And if they aren't, not all of the elements match, and then I go and I report the error that these guys mismatch at this spot. Here's what the value should be. If all of the elements match, I return success. Otherwise, I return mismatch, which was this guy back down here, who was a failure. Any questions about this, like equals? So then over here and say, for example, like the constructor tests, I have some test container over here, right? That's the type. That type is defined back here in test vector. So test container is a vector of pairs where the first thing is a matrix vector, your guys' class that you're writing, and the second element is a DV, which you can see up here is a standard vector of doubles. So what I do is I create your matrix right here that says, hey, I'd like a matrix that contains 3 tens. And then the answer should be a vector that contains 3 tens. And then one with 20 17s, and then 5 9s. And then for each one of my tests, I check to see that your matrix or your vector matches the standard vector's contents. So it's just verifying that the things are the same. Any questions here? Then we have ones that are constructed using size only, or ones that are constructed using values. So I'm just double checking this to make sure that everything works as intended. Because if you don't double check, you don't know whether it's actually working or not. But you should kind of like look through here and be like, well, these tests are kind of like stupidly simple. And yeah, they are stupidly simple. They're supposed to be that way. They're just supposed to be verifying that what we expect to happen is indeed actually happening. Any questions here? Let me go make sure my CMake list is correct. Okay. This should have been out here. And this should not exist. And we can reload our changes. And then this guy should stop complaining at me. If we look back here, notice like I'm not actually using my own main. So that's why this main over here, he exists, but he's not being used over here in this executable. He's using the main provided by CoolTest. As you can see, this project is not a part of my project, but if you did want to write your own like main, this is what the CoolTest main basically looks like. It inits the CoolTest and then it runs all the tests. See over here, it's not complaining anymore. And if you build like you saw before, it takes a long time because there's a lot of like templated code that goes on here in the CoolTest. And then we could run it and we could see that, oh, yay, we passed all the test cases. So all that wraps up. One kind of like weird thing about the failures in CoolTest or like the asserts is that it's only going to fail that function and not the entire test. So let's say you're writing a test case, that test case calls a function, that function fails via like a call to like, assert, it fails, or it calls fail. The rest of your test would actually keep running unless you check to see if that subfunction that you called has indeed failed. So ways that you can get around that, or if you want it to fail when that subfunction fails, you can use assert or expect no fatal failures in the statement, or you can check has fatal failures to see if that has happened. So what you can do for the assert expect no fatal failure is you can say like assert no fatal failures and then put your code in here. That code will then run, and if there is a fatal failure inside of here, then we will terminate the rest of this program. Or you could use call some subroutine that fails. If it has a fatal failure, you fail yourself. Either way will end up working. The gmock matchers are super useful. I do use them occasionally. The full list of matchers can be found here. I probably have to search matchers. So again, they have like double equals, float equals, double near. They have strings. Does it contain a regular expression? Does it end with something? Does it contain a substring? Does it match some regular expression? Does it start with something? So these guys are all useful. Or you can have like some container matchers. Hey, does this container equal this other container? Does this container contain these values? Is each of the elements in this container assert or agree with this matcher over here? So it could be really useful to use these and investigate into them and how they work. It could greatly reduce the sizes of your tests if you do so. So an example might be like assert that some string starts with hello. This would verify that the string does indeed start with hello. Sometimes, though, you might have values that you want to pass to your test and have it run over different tests. You can do this one way is with the parameterized tests, And so you inherit with testing, test with param t. T is going to be the type that you want your test to contain. Then you use test p, test fixture, test name. And then inside you use get param to get the parameter. And then to actually create an instance of the test suite using some type, instantiate test suite p, the name of this particular instantiation, like what type may be, the test suite name, and then the parameter generator, the thing that's going to actually create the parameters. The instantiation name has to be unique, and it's going to actually be added to the front of the test suite name. This will allow you to test the same suite with multiple different values each time. So back here with the simple tests, right, I want to be able to test my code with different integers. So over here I have fast fib test param is equivalent to testing test with param integer. This is just a shortcut so I didn't actually have to write out a class. So over here, here's test p. So fast fib param test. And then we want to say that then over here, it's going to be the actual name of our test is fast fib matches the slow fib, so we're verifying that these things are the same. So then I assert equal that the slow fib's get parameter is equal to the fast fib's get parameter. They return the same thing. And so you can pass in those different values to make sure that they're working. And then over here you can see we're actually going to create my test suite. This it's called base test is the extra name to be prepended. The test suite name is the fast fib param test right here. And then the thing that I want to generate is a range of values between 0 and 10 to try it out with. So when we run it, it's actually going to be tested against all those different things. And you can see that it ran it with different values. So you can see here it's like, okay, the base test, fast fib param test matches 0, okay, 1, okay, 2, okay, verifying that they're all working. And then we also have our simple ones that are working on the slow tests. This output might not always be the most useful form for you to look at it in. So what you can do is you can go to run and then edit configurations, and you can add a new configuration, and you can make it a Google test configuration. And we want to use all the suites. Our program that we want to actually run is simple tests. The name of this thing might be like run all tests. Say OK. And now when I use this configuration, it's going to give me a little bit nicer form to look at it at. And that we can see it down here. You can see which ones are passing and which ones are failing. So let's say we made a mistake. Say in our slow fib, maybe we had this base case return 2 instead of 1 for whatever reason. And now when we go ahead and run, you can see that we got the output here that these things are wrong, and we can also see like the failures over here. And you can click on each one to get the information for that particular test case. And you can see it's like we expected the equality of these values, 8, but it's actually 16. So 8 and fibbing, slow fib 5, but it's actually 16. The values weren't the same because we had the error. We get rid of our error, and then everything is all cool again. Any questions so far about using Google Test? It's going to be something that you actually have to practice with to kind of like understand how it works and to get good with it. But taking the time to learn how to do this and write your own tests is going to save you a lot of time overall. One form of like program development that's recommended sometimes is like test-driven programs. So what you do is you write your tests first. Like this is the behavior that I expect. And then you go write your class to behave like you expect it should. So you kind of start with a test first, and then you write your class instead of writing the class first and then verifying that it works. And that can tend to lead to better designed programs. So the parameter generators are range, so begin, end, step, values, you list out your values, a container, so if you had like a vector or a map, you could put the values in there. They could be an iterator pair for the beginning and ending over some container, bool for true and false, and then combine, which yields all possible combinations as a tuple of G1, G2, G3. So we're just going to look over some more tests. Let's say, for example, we wanted to open our doubly linked list. So the doubly linked list one is a little bit more complicated because it does use that parameterized testing. So I have this function that kind of checks to see whether the linked list matches an iterator of the same value. Or a linked list matches a vector of the same value. So what I do is I check that their sizes are the same, and I complain if they're not. Then what I do is I create forward iterators over both your class and the vector. And then I go through those elements forward to see if they're all the same. Then I create reverse iterators, and I go through them in reverse to see if they're all the same. This little part over here that kind of checks whether they're going forward correctly or not is we have our iterators, and while they're both not equal to their corresponding end, we keep going. And if the values don't match, we complain that the values don't match and we stop. And technically this plus plus should have been right down here to give you the right index. Then what I do is I make sure that the iterators are actually at the end, because I don't know which one's going to cause it to stop up here in the for loop. I just know one of them causes stop, either your iterator or the vector's iterator. So then I check to make sure that they're both at the end, because they should both be at the end. You should finish stopping at the same time if you reported the same size. But I'm just double checking that that makes sense, that you actually did that. And so here we say, oh, hey, if they don't both equal the end, the iterators, did not end at the same time, despite the fact that your container said they had the same number of elements. Because if they had the same number of elements, when you iterate through them, the iterator should end at the exact same time. So if you were going to be writing tests, what would your tests look like? What would you do? Given that you want to test your doubly linked list class. Like, for example, let's say we started over here. What would you want to test in this function for this constructor? How would you go about designing it? This is, again, the constructor that takes a vector, and you're supposed to create a doubly linked list that has the same values. It's not a complicated test. Yeah, you create a doubly linked list using this constructor, right? So you create a vector, right? You create a doubly linked list from those values. Then after you create that doubly linked list, what should you do? Check if they're the same, right? And that's all the test is really going to do. So if we actually go back to the test, here is our constructor test. And because this is parameterized over the types, some things get a little bit more complicated because you can parameterize over type as well as parameterize over the parameters. So over here, I have my constructor arguments for numbers, 1, 2, 3, 4, 5, 6, and for strings, Bob, Cat, Sally, Man. So over here, here's my type test. This is how you can create tests that work over different types. And so down here, I call the vector constructor over the particular type that I'm trying to do. And then I check to see that they are the same thing, right? What would you do for the empty constructor? Well, you create a doubly linked list that's empty. You create a vector that's empty, and you see that they're the same, right? But again, that requires checking that the sizes are the same, that the elements in each position are the same, and that when you iterate through them forwards and backwards, you get the exact same things, and that the iterators end at the exact same times. So it gets somewhat complicated. Well, not complicated, but you know, very detailed, that you really want to check this, that everything is happening like you expect it should. So let's say we want to write a test that tests to see whether the let's say we wanted to check to see if the push front method was working. What would you do? Well, again, so we have to like push the element to the front and then check to see that the element's there, right? But in order to verify this is working in all contexts, what general forms of vectors should you try pushing to the front of? Well, yeah, type T, yeah, but like I'm not talking about like in terms of types, but there are two, like you know, linked lists you'd want to try pushing to the front of. An empty one, right, to see if it works pushing to the empty one, and a non-empty one, right? Because those are going to be like two kind of different cases. One is like an edge case, right, the empty list. One is like the normal case, it's not empty. So you need to verify that both are indeed working. So if we go to our tests, again, here are some more like values that I create to be pushed to the front. So here's a test that just tests pushing to the front once onto an empty list, right? And then I call your front to make sure that they're working, right? Does that work correctly? The other thing that I do is I push front to the once, and when I push front to the empty list, right, the first element and the last element should be the same thing, right? So I double check that. Oh, when I check front and I check back, are they identical? Which they should be, and you check that. These ones were both empty lists. So over here, there's push back, which is, you know, doing more or less the exact same thing to see that there was nothing there. Then over here, we create an empty list, and then we keep pushing to the front a whole bunch of times. And after each push front, I verify that they're the same values at the front. And then after all the push fronts are done, I verify that the linked list and the vector are the exact same thing. And then we do the exact same thing with push back. I keep pushing back, and every time I push back, I make sure that the value I added to the back is actually there, right? And then I verify that the lists are the same. I guess I didn't actually do a test. You can see that all these tests right here maybe are slightly weaker in that they always start with the empty linked list to do the pushes on, but it might have also been useful to call one with your vector constructor and then do a push front on it and a push back on it to see that it's the same. And then down here, I tried doing like push front, push back, push front, push back, push back, push front. And then again, verifying that everything's the same after I do a push front and a push back. Does this make sense? So when you're like writing your final project, you can do this as well, right? If somebody shoots the ship, what should you check? That I got hit, right? When someone shoots all the spaces on that ship, right, it's all completely shot up, what should you check? That it's destroyed, right? If somebody shoots at a place that's not a miss, or that doesn't contain a ship, you should check that it misses, right? So you want to verify like every step along the way that what you expect is happening, right? If somebody shoots at position 3-3, what should you do? Check that 3-3 gets hit, right? Either a miss if there's no ship there, or a hit if there's supposed to be a ship there, right? But you need to like verify that what you expect is happening is indeed actually happening. It's the same thing with debugging. And if your test cases are going wrong and they're not working and they're failing for some reason, throw them into the debugger and you'll be able to look through that particular test case, you know, set a breakpoint there just like normal, and walk through the test case and see what's happening. Where does it break? Where does it go wrong? And again, you're just verifying that what you expect to happen is indeed actually happening. So like, again, I do recommend looking through these test cases for both the vector and the matrix, or the matrices test cases, as well as the doubly linked list to get an idea of what you can do with Google Test. because again, it's a really useful feature. It will save you a lot of time if you actually do use it, but it does take a little bit of time to learn. I will let you know that I was kind of like abusive with Google Test here in the matrix stuff, and maybe I didn't use it in a way that's intended. So I'll show you some weird stuff that I did. So over here, for example, in test vector, where is it? Oh, it's like say test vector and scalar. If you look in here, there's this, which this seems very frightening. And maybe in some ways it should be very frightening. So what these are basically paths to the files of test cases that I wanted to generate. So because I had a working solution for my program, but I can't give you a working solution for my program, what I wanted to do was run my program with some input, have it produce the output, save it somewhere, and then check against it. So these are all the paths to the files, and I wrote some code to make all this stuff, so I had to type it out manually. But what you'll see over here in the cmake list.txt is something a bit interesting. So over here, I declare some variables like input vector dir. These are where my inputs are going to be at. They're going to be in this directory. Cmake allows you to specify like the current source directory that you're in. So the source directory that I'm in right now is vector. So regardless of what computer that I run it on, this will give me the correct absolute path to your computer, on your computer. So I don't have to hard code it, which is great. And then I do the same for where the solution vector should be, the vector and scalar directories, and the vector and vectors answer should be. And then again, I get the add, the minus, the multiply, the divide directories. And then I do it for add, minus, and multiply for the vector and vector ones. And then, you know how we saw like the pound defines on Wednesday for macros? You can actually set command lines on the compiler to generate macros for you. And so what I'm doing over here is I'm directing CMake to create some macros. And then the names of these macros should be input vector directory, and it should be equal to whatever this vector, whatever this path is over here on the right-hand side. So that when I substitute it in the test code, I'm actually going to have that correct path. And then again, do that for each one of these. So I have the path inside the C code to be able to get to it, regardless of whether it's running on your computer or my computer. So this is probably not how Google Test should be used, though. But I wanted to use Google Test for you guys to make this kind of be a little bit more interesting, like it should be. The reason why like there were so many test cases that got generated was like, well, I might want to try doing this like, you know, with 3 different vectors, right? But maybe these 3 different vectors, I want to try adding 5 different scalars. Well, that's 15 tests right there, where I have to write out what should be the input, what should be the output. 15 times for one single test, which is kind of crazy when you just think about the small number of things that we're doing. So I had the computer help me do this by writing another program to generate all this stuff. So like here's a test where we do something like vector and scalar, and we're doing vector plus scalar. So I go through my plus test cases, which are over here. Like here's the plus test cases. Here's the minus test cases, you know, multiply test cases, and the divide test cases. And then we have the scalar minus vector test cases, right? There's a ton of them. That's why I had this guy collapse down, so I don't have to look at the ugly mess. So we go through each one of those test cases, and we load the vector from that file that's supposed to be in there. Then we load the answer from the answer file into a double vector, like an std vector of doubles, and then I add the 2 values together and I check to make sure that they're equal to the answer. So like maybe like a simpler test might have been you create a vector that has just like 1, 2, 3, and then you add 5 to it, and then what should the answer be? 6, 7, 8, right? So you would just verify that those 2 things are the same. That's how testing goes. It's what do you expect to be happening is indeed actually happening. And then make sure that you test the edge cases too. Those are like the hardest things to remember to do because you don't think about them, right? Like if you think about for your doubly linked list homework, what tend to be edge cases there? We're doing operations on your doubly linked list. Depends on the function, but you might be like, well, the empty list tends to be an edge case, right? Or if you go from having a full list to having an empty list, that might also be an edge case, right? But you also need to make sure that you test like the stuff that makes sense. So for example, if we were looking at like the insert method, we'd want to try like inserting at the front of the list, at the end of the list, in the middle of a list, inserting into an empty list, checking all those things work. For erase, we might try erasing the first thing, erasing the last thing, erasing something in the middle, erasing the only thing in the list to make sure that they're all working. And then you kind of also want to verify that things are working nice together. So you might try like doing inserts and then erases and inserts and erases and making sure that every time you keep doing it, everything is still correct and everything is still functioning correctly. Does that make sense? You guys have any questions on the Google test? Did you guys read the documentation? Okay. If you do plan on using it, do read through the documentation. I think the tests here, they look fairly straightforward, right? The hardest thing that I had using Google Tests was figuring out how to get it set up and installed. And so like if you follow like that CMake list, it will make it so it'll be really, really easy for you to get it up and running. If, for example, we go back to the simple tests, you can see like our CMake list looks very similar to the one that was on the homework or on the slides, right? So we find threads, we include fetched content, we declare Google test, right? We create the property. If it's not populated, get it, add the subdirectory in, and then to our executable, for simple tests, we put in test.cpp, fibbing.cpp, and fibbing.h, right? The files that made up our tests, as well as the code that we wanted to test, which is the fibbing stuff. And then over here, we targeted the linked libraries, gtest, gmock, and gtestmain. This one we can leave out because we're not using gmock in our current test cases, so that one could be gone. And then we set some compile options like normal, the wall, and the error. Anything else? Okay, so Monday we will wrap up with CMake a little bit, and then we might get into some more advanced topics like constness and how you can actually remove constness. And if we still have time, we'll tell you how to write functions that accept any number of arguments with any number of parameters. Oh, also, I will be staying a little bit later today at office hours.